The topic of my presentation is real-time digital image correlation coupled with an anti-buckling device for cyclic tension compression testing of lightweight materials. I'll start with a quick bio. Thank you so much for a detailed one, so I'll just quickly go over it. I'm basically from India. I did my mechanical engineering there, and I worked for Honda two-wheelers there before coming here in 2015 and joining Clemson University for my PhD. So with over 5 years of experience in material testing, primarily focusing on the integration of DIC with the standardized and custom tests, I joined FADI AMT in 2019 as a material testing lead. About FADI AMT, we are a material testing lab and research consultancy in Greenville, South Carolina. We perform standard testing to support our R&D efforts for our clients, but our niche is custom material testing which is conventionally considered as difficult or perceived as impossible. This is a slide showing some cool test images and DIC strain snapshots to show what we do. And with this, let's open the topic for my presentation. Sheet metal stamping, as we all know, is the workhorse of the automotive industry. Majority of the automotive body components are produced by metal stampings. It is the go-to process because it is compatible with a lot of advanced materials, it's fast, and it supports high production volumes, and thereby it is also cost-effective. But like any other process, stamping has its challenges too. If we come to die design and manufacturing, it is a challenging and an expensive process. If the die design doesn't account for the material behaviors like anisotropy and springback, etc., it becomes an endless process of trial and error. And the introduction of advanced high-strength steels and aluminums makes it even more harder. There are several other problems, but the problem that we are going to address today in this presentation is springback, which is basically the elastic recovery that a metal experiences after it is unloaded. If you see the picture on the left-hand side, the profile or the part on the left shows a final product with springback, and the right-hand side is the desired profile. There are many well-researched material models and finite element tools which are capable of predicting the springback behavior of materials after the stamping process, and those can help eliminate or lessen the fixing in the die and get us to a first-time right die design. But these advanced and really complex constitutive models like the Yoshida-Omori model, which is really popular in the industry, so these models are only good if the experimental data that is fed into them is good. So the main bottleneck here is obtaining high quality, accurate experimental results. This is a summary of the tests that are required for feeding into the springback prediction models, especially Vayu model. The tests, there are mainly 4 tests. It's a uniaxial tension test, very simple. Then it's a uniaxial tension load-unload test, which is used to determine the modulus decay in the material as a function of strain. We need uniaxial compression test to study the tension compression asymmetry, and the cyclic tension compression test, which is the most difficult of them all, and it is used to quantify the Boschinger effect. Now, the main challenge here is that the monotonic compression tests and the cyclic tension compression testing have a big problem, because the sheet specimens are subjected to out-of-plane buckling when they are under compressive loads. And this also makes it more challenging that the reliable strain measurements are very difficult to obtain on such setups that are already listed and discussed in the literature. There are several notable works in the literature that propose methods and techniques to counter this problem, but unfortunately none of them cover all the issues. None of them present a reliable strain measurement method, and of course, none of them talk about the uniformity of the strains in the samples. In addition to that, none of them are tested on advanced high-strength steels of 1000 megapascal plus tensile strength. So this is our research question. We need a reliable test setup which can prevent out-of-plane buckling and also provide high-quality full field strain measurements to address all the issues. So today we'll be presenting an anti-buckling device which is capable of putting side force on the specimen which is measured and controlled. In addition to that, it is coupled with a 3D DIC in conventional as well as real-time mode. The target was to achieve high compressive strains of more than 10%, and we tested this over two materials which are DP980 and a medium strength aluminum alloy. So the outline of the presentation looks like this. I'll be going over the design of the test fixture, and then we'll be discussing four types of tests that I already mentioned, and they were tested over DP980 and aluminum alloy, and we'll conclude with the analysis of our test results. So the experimental setup. The experimental setup features an anti-buckling device which is capable of fitting over any electromechanical load frame, and there are many features and advantages of the device over conventional setups, and we'll discuss this in the upcoming slides. We also tried to implement 3D DIC, actually a couple of DICs in the setup, and we also use them in real-time control mode. This is a picture showing the full test setup, and I'll be going over some important features of it in the next few slides. So the first important thing here is side force control and measurement. So the setup is basically a rigid cage structure with the specimen held between two contact blocks and plates. And the side plates or the blocks are attached to a pneumatic cylinder, and the amount of pressure that is applied to the pneumatic cylinder controls the side force, and that force is also measured with the load cell that's connected along the force direction. Next thing is the self-centering mechanism. So the whole cage can move freely in the horizontal direction. This enables self-centering, and this also makes the device capable of accommodating sheet specimens of technically any thickness. The next important thing was the DIC systems. So we did use two different types of DICs. First was a custom FADI AMT extra high resolution 2D DIC system, which gave us 6 microns per pixel density. And this one was used in a conventional mode. The second one that we used is a commercial GOM Aramis 3D DIC system, which was used in real-time mode. This is the field of view for the DIC, and the specimen was captured in the thickness direction or sideways. Here comes the advantage of using a high resolution camera that made the measurements over such a small surface really accurate. The strains were tracked on a virtual extensometer of 16 millimeters throughout the test. Now, what exactly is real-time mode that I've been talking about for the last 10 minutes? So real-time mode DIC is that the DIC is capturing the images. Also, it is processing the images and getting the strains out in real time. And those strains over this 16 millimeter long extensometer are converted to an analog signal and fed back into the load frame controller. Now the load frame controller, instead of taking the crosshead movement as its reference, it uses these strains to trace a set cyclic path for load reversal at precise strains. This type of real-time mode was used for cyclic TC tests and the uniaxial tensile load-unload tests. I'll quickly go to the experimental results. As I said, the tests were done on two materials, DP980 and a medium strength aluminum alloy. Both were automotive grade. The uniaxial tension results, the tests, all of them were done on a custom sample, and the uniaxial tension tests especially were done with two configurations. One was without any side force with the anti-buckling plates completely open, and the second configuration was with side force. So this side force reading was taken from the tests that will be discussed in the subsequent slides, which are monotonic compression and TC tests. And the purpose of doing this testing in two different configurations was friction correction. Since the contact blocks are in contact with the specimen touching it, there are friction forces that are involved here and that need to be accounted for and corrected for. We can see in the curves down here that it was a small amount, around 1.8% correction, but this was done in the compression as well as cyclic TC tests that are discussed later on. The next results are for uniaxial tension load-unload tests. So these tests are done basically to determine how the Young's modulus or the elastic modulus of the material looks like after a certain pre-straining is done. So the modulus of any material is considered to is known to decay with the elastic strain, and these tests are really important for our prediction of springback. So the loading and unloading curves for both the materials were done at pre-strain levels of 1, 2, 3, 4, 6, and 8%, as you can see in the picture. And you can clearly see the difference in the material behavior of the two. On the left hand side, if you notice, the unloading and the loading curve are very non-linear. You can see the two lines very separate, far apart. But on the right hand side, the loading and unloading is basically traced on top of each other. So this is one of the differences that is observed in the two materials. I'll show a quick video for this test and how the strains evolved and how we've put a section in the middle which is showing the strain homogeneity on the sample during the test. So the help of DIC here is that we are able to monitor the strains in real time and do the load drop at precise strains to whatever we want. Also, we get an understanding of the homogeneity of the specimen, of the strains over the specimen as it is being loaded. So the elastic modulus results that came from these tests are shown here in the curves, and they were used to fit a very popular equation in the literature, which is an exponential fit, and we can clearly see that there is almost a 20% drop in the elastic modulus that takes place after a plastic strain of only 3% in DP980, while it happens over a strain range of 8% in aluminum alloy, and this is of course owing to its high uniform elongation. The next results are monotonic compression tests. So our target was to achieve compression tests, strains of over 10%, and we were able to go well beyond that. A side force of 4 kN was found satisfactory for DP980, while only 2 kN was enough for aluminum alloy. So we went on by with a low force and kept on gradually increasing it while monitoring the specimen after the testing for any signs of buckling. That's how we came to these values for the side forces. And the curves shown here are already corrected for the friction effects that I discussed earlier in the uniaxial tension case. Again, I would like to show a quick video of the compression tests and how the strains evolve as the specimen is being compressed. And you can see that there are visibly no signs of buckling, any mode of buckling here. The next results are for cyclic tension compression tests. So the tension compression tests were again done at the same side force of 4 kN and 2 kN, and we went really aggressive on it, and we did 3 loops at a strain reversal of 2.5, 5 and 7.5%. And you can see the anti-buckling setup demonstrates a really high level of repeatability in the test results for both the materials. So the results are really on top of each other for the first loop, and from the second and the third loop you do see some variation, But that is because of the inhomogeneity in the specimens and the strain accumulation in the specimen, which is really straining and accumulating over the cycles. This is a video showing the strain accumulation on the surface in a TC setup, in a TC test. And on the right hand side, the top plot is also showing the side force. The side force you can see is technically near constant during the whole test. So that was a big plus for us, that the amount of friction is technically constant, so the friction correction was easier for us. I'll move ahead to the analysis of results. Now here we've plotted the TC tests as well as the uniaxial tension and compression tests on top of each other, and we see clearly that the two materials respond to the tension, compression and cyclic loading in a very different way. If we compare the DP980 on the left to aluminum alloy on the right hand side, both show large tension compression asymmetry. The red curve is higher than the black curve, and that is typically after yielding. So the compression curve has a very different N value and a very different slope basically, which has to be accounted for. The next important thing is the huge jumps in the flow stress level from one cycle to other in case of aluminum. See, the flow stress from one cycle to the other is jumping really quickly in aluminum, while in the DP980 case, it looks like it's merging with the uniaxial tension case. So there is basically no effect of cyclic loading on DP980. But it's not as simple. DP980 shows really early re-yielding for each new cycle, which is not observed in aluminum. Aluminum is showing a very high yield stress for each new cycle. So this again shows how important it is to get accurate material properties for prediction. The next advantage that we got from the DIC is the full field strain contour. These are snapshot at several points of interest at 0, 2.5 and 5 and 7.5%, and you can see the level of inhomogeneity in the specimen at increased levels of strains, which is very evident in the material here. We put a cross section here on the DP980 specimen that's shown here, and you can see the right hand side bottom plot is showing the strain evolving with each cycle, and at 7.5% it's so inhomogeneous. So this is the kind of information that's really valuable and which comes only with the use of a DIC in such kind of tests. Aluminum also shows same kind of inhomogeneity, but it's not as severe as in the case of DP980, and that's owing to its high uniform elongation, which is 25% for aluminum as compared to 7% for DP980. The final remarks here are that we presented a new anti-buckling device with many features. We integrated DIC in both conventional and real-time mode. The results really show the importance of these tests in revealing complex material behavior. And such information is very critical, and it's needed to feed complex springback material models such as YU model. For more details, you can refer to the technical paper, which will be available, I think, next month. And thank you so much. I'll open the floor for any questions.